How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at 5.5a, calorimetry. So our objectives will be to solve calorimetry type problems, which means determining the change in enthalpy of a reaction from the data for constant pressure calorimetry and constant volume calorimetry. All right, so basically you have a reaction, and the big question is, what's the energy change of that reaction? Is it absorbing heat? If so, how much? Is it releasing heat? If so, how much? So we're going to quantify that information. So the big idea is if we measure the temperature change of our system and determine how much energy was absorbed or released, we'll be able to determine, the heat. So this process is called calorimetry, right? Calories, you think of energy, right? They're in our food. The calorie, and metry means to measure. So we're measuring the energy. So constant pressure calorimeters can be high-tech fancy stuff, or most of the time when you're in like chemistry lab, we'll probably do some low-tech versions, which is just going to be two styrofoam coffee cups stacked on top of each other with a thermometer inside, because that, for what we're doing, is fine. So how it works, big idea is you have dissolved reactants and you put it into the vessel, right? The styrofoam cups. The reaction occurs and heat is either given off or is absorbed by the reaction. So now this causes the temperature to change. If energy was released, the temperature of that water goes up. If energy was absorbed, the temperature of the water goes down. So if you can measure the change in temperature, you can determine how much heat was being given off or absorbed. So first thing we need to understand is this thing called specific heat, and it's how much energy it takes to heat 1 gram of a substance 1 degree Celsius. So every substance has a different specific heat. Different materials, different specific heats. Water, for example, has 4.18 joules per gram degree Celsius. So if you want to heat up 1 gram of water 1 degree Celsius, you need 4.18 joules. Whereas aluminum, for example, is 0.90 joules per gram degree Celsius. So they got different specific heats, and they are usually given by the lowercase c. So c, that is the specific heat. Okay. So if you know the amount of substance and the change of its temperature, you can determine the heat change. So the math, again into that. Q we're going to use for the heat exchange. That's going to tell us the heat gained or lost. The M is going to be short for mass of the stuff that changed temperature, usually like water for a lot of these problems. And the delta T is going to be the change in temperature. Remember, delta is a symbol for change in and whatever comes after it. So delta T will be a change in temperature. And little c is for a specific heat of a substance in this scenario. So we get a formula that looks like this. Q equals mc delta T. mc delta T, right? So the heat is equal to the mass times the specific heat times the change in temperature. So let's take a look at a math problem. It says a chemistry student dissolves 9.02 grams of sodium hydroxide in 200 milliliters of water at 19.5 degrees Celsius, which is, into the calorimeter cup. As a result, the temperature of the water increases to 31.7 degrees Celsius to determine the heat change for this reaction. Well, all right, I'm going to have to use, don't draw there, use my formula. Q equals mc delta T, and it's asking for the heat change, so I'm solving for Q. So it's set up how I need it. So now I got to figure out, well, what is the mass of 200 milliliters of water? Well, this is something you should just know. The density of the water is 1 gram per milliliter. So the 200 milliliters is really the same thing as 200 grams of water times the specific heat of water, which we should know as 4.18 joules per gram degree Celsius. And then we need to times it by the change in temperature. Well, it was at 19.5 and went to 31.7. So I can do that math real quick. Minus 19.5, and I get 12.2 as my change in temperature. So all that will be times by 12.2. And then I plug and chug, and I get this answer, 101,992 joules, right? Because this 12.2 is degrees Celsius. That cancels out down there. My grams cancels out, and my units agree. I have found the answer. Boom, shakalaka, right? So that's how you solve these problems. We also have bomb calorimetries, where you use a bomb calorimeter, and they're a little different. This is really helpful for like combustion. It's a reaction of interest. We want to know how much energy a fuel has. When we combust it, we can do bomb calorimetry to figure that out. So the big idea is you have this bomb, essentially, which is going to contain all your stuff under pressure. You have your sample right in here, and then you have a filament that's going to get heated up. So you got electrodes here, which is going to heat up that filament, and you have a bunch of oxygen in this vessel as well. And then you pump it up, and then you start burning it, and it starts giving off energy, right? And all that energy gets absorbed by water. It's usually filled with water, and that water acts as a heat sink. And then we have a thermometer, which is going to measure how much temperature change occurs because of that reaction. So heat something up with oxygen, and it will burn, and then you contain it in that bomb, and then you let it all come to the same temperature. You got a stir here, which is going to help it get to the same temperature throughout, and then you record your temperature. And if you know the heat capacity of the bomb, which is like, this whole thing, if you know how much energy it takes to raise it a degree, then you can figure out how much energy was being released. So the heat capacity is something different than specific heat. The heat capacity is how much energy it takes to change the temperature of an entire system. So this is different than specific heat, and it's usually given as a capital C. So capital C versus little c, they're different. So this is usually determined beforehand by a reaction standard. You do a reaction that gives off a certain amount of energy. You look at how much the temperature changed. So now you know how much energy it takes for each degree Celsius, right? So the units on heat capacity are generally joules per degree Celsius, whereas specific heat, there's something different. So bomb calorimetry is a little different too. It's a constant volume. The other one, we had an open container, right? We had a styrofoam cup that was like this, and it was more or less open to the environment, so that was like a constant pressure. But with the bomb, what's being held constant is the volume, because it's sealed. It's completely sealed. It's not letting anything in or out. So when we get our heat transfer, that's equal to our change in energy. And the difference between delta H and delta E is usually very small for what we're doing here. So we usually, don't have to worry about it, and we're not gonna. It's usually less than 1%. We're not gonna worry about that. So here's an example of a bomb calorimetry problem. It says a 0.500 gram sample of naphthalene is burned in a bomb calorimeter at an initial temperature of 20 degrees Celsius. After the reaction, the final temperature of the water is 26.40 degrees Celsius. The heat capacity of the calorimeter has previously been determined to be 420 joules per degree Celsius. How much heat has been released? All right, so for this, our equation gets a little bit simplified. Q, which is our heat, is going to equal capital C, which is our heat capacity, times our change in temperature. Right, so that is the heat capacity, which they tell me is 420 joules per degree Celsius. So now we just times it by the delta T. Well, it went from 20.00 to 26.40. So easy math there. 6. I just can't write the wrong. 6.40 degrees Celsius, right? Degrees Celsius cancels out. You're left with joules. You plug and chug, and you get 2688 joules. So that's how much heat has been released. Okay, so specific heat versus heat capacity, you might be confused at this point. Remember, specific heat is for a specific substance, right? So it can be like water. What is it for H2O? Well, it's 4.18 joules per gram degree Celsius, whereas heat capacity is for a whole system. You're talking about the system as a whole, and the units on that are just going to be joules per degree Celsius. Right? Because the grams, we're not worried about that because we're looking at the whole system. Okay, so that's the difference. It's the difference between lowercase c and capital C for our abbreviations using our symbols. So summarize, what are the following symbols for? What's Q, M, little c, big C, delta T? What are all those? What do they mean? What is the difference between heat capacity and specific heat? And how does calorimetry work? What's that all about, and how does that work? So that's hopefully what you're able to answer. Hope you have questions. See you in class. All right, okay, bye.